Now, multiplying vectors, that means multiplying a vector by another vector, is not defined in the first place. So there is no natural operation giving a product of two vectors. Instead, one considers two different types of multiplication. Because each of them has its importance in dealing with vectors. The first one is the so-called scalar product, also called a dot product. Okay. The scalar or dot product of two vectors is defined as follows. You have v1, v2, v3. You put a dot between them, so that's why we have the dot definition, or the name dot. That is defined to be the sum of the products of the corresponding components. Okay, so you take the corresponding components, multiply them, and of course, you get a scalar. Firstly, v dot w is a scalar. It's not a vector. That's why one calls it a scalar product. Well, of course, from the definition itself, if we take the dot product of v by itself, we have v1 square plus v2 square plus v3 square. That is the length of the vector squared. And so, a dot product is always positive, and with itself, and it is 0 if and only if v is the 0 vector. Okay. It's easy to check these things. Now the other operational properties, the dot product does not depend on the order. Okay. Well, directly from the definition, we see that. If we multiply a dot product with a scalar, it's the same as lambda v dot w. Of course, lambda times v is a vector, so we can take the dot product. Or, it would be the same as lambda w. So it's not important where you put your lambda. You have distributional properties. That is, if you have lambda plus mu, these are scalars, times v dot, let me see, that doesn't say anything. Yeah, Okay, let me correct it. So if you have u plus v, okay, dot w, you have u dot w plus v dot w. Okay, you can put it on the other side, certainly, and it would be the same as w, because you can change the places, dot u plus v. Okay, and roughly that's fine. Okay. Now the scalar product obeys a very nice inequality, which will tell us a few more things about the norms of vectors. Namely, we have the following theorem. Let v and w be vectors. Okay. I don't care where, actually. Then one has the following. Firstly, the dot product in absolute value is bounded by the product of the norms of the vectors. Okay. This is called Cauchy-Schwarz inequality. And two, the sum, the norm of the sum of two vectors is always less than the sum of their norms. This is called triangle inequality. Okay. The Cauchy-Schwarz inequality is quite simple. If you have one-dimensional vectors, that is, if v and w are numbers, obviously you have equality, because then these norms mean absolute value. Well, absolute value xy is absolute x times absolute y. But in higher dimensions, even in R2, okay, you have to work a little bit. In R3, this becomes quite complicated. So our proof then is quite valuable in this sense. For one, okay, for any number in R, okay, consider the norm of v plus lambda w squared. Now, this is the length of this vector, so it is not negative. It's squares, of course, is positive. So this is always positive in the first place. It's true for every lambda. But that's the same as v plus lambda w dot the vector v plus lambda w. Because dot product of the vector with itself was the square of the norm. Now, using the properties of the dot product, we can distribute them. That is, this is v dot v plus v dot lambda w plus lambda w dot v plus w dot w. In short, it is length of v squared plus twice lambda, let me see, right, lambda times v dot w plus norm of w squared. Something is wrong. What is wrong? Here, of course, we have this. So we have here a lambda squared. Now, at this point, forget about the vectors v and w. Think of lambda as a variable. This, of course, is a second degree polynomial in lambda. Everything else is a coefficient. This was true for every lambda. So, okay, if a polynomial of degree 2 is always positive, okay, it means that the polynomial must have a discriminant which is not positive. Okay. Of course, if the discriminant is strictly positive, the polynomial will have two different roots, and this will say that somewhere it will take negative values as well as positive values. So the discriminant must be negative. But discriminant is, okay. Now this is the polynomial. So we have b squared, that is 2 times v dot w squared. Well, I mean, just squared is enough. B squared minus 4, okay. A times C, well, A is norm of W squared, C is norm of V squared. And it is negative. Okay. This says that the absolute value of V dot W is less than length of V, length of W. So it finishes the proof. For the second part, the triangle inequality, okay, let us look at the case where lambda is 1. That's to say, let us look at V plus W norm squared. Well, it is V plus W dot V plus W. It is, okay, I will not go into details. We did it once for lambda. So that is the norm of V squared plus twice V dot W plus norm of W squared. Now this is less than two times the norms multiplied. Okay, this is because by Cauchy-Schwarz inequality, which we proved, plus W squared, which is of course norm B plus norm W parentheses, squared, take square root, and then we have the triangle inequality. These are simple proofs, but they are making a very difficult inequality to be shown in a simple way. Okay. Well, the next theorem, or property if you want, before passing to examples, will be the following. This is a very important aspect of the dot product. Okay. One has that the inner product W is the length of V, the length of W times cosine of alpha, where alpha is the smaller angle, okay, between V and W. Now, the proof rests on the so-called cosine theorem. Now consider the picture as follows. I will draw it in plane because when you have two vectors, okay, okay, and when you start them from the origin, then the two vectors lie in some plane. So this is not simplifying, it's just observing this fact. Okay, so say we have two vectors, okay, V and W. And this is the angle alpha between them. Okay. Now, call this C, that's the distance, C. Okay. Then, by cosine theorem from high school, we have that the squares of the lengths added okay, is the product of these sides. Yeah, sorry, that would be right, C squared plus the product of the two sides times cosine. This is a generalization of the Pythagorean theorem, actually. If alpha is pi over 2, if it's a right triangle, then you don't have this term, so it is the Pythagorean theorem. Okay. So this is the cosine theorem. Now we observe that okay, C actually is the length, okay, of the vector connecting these 2 points. But this vector, okay, is nothing but, if you draw it like this, okay, that is W minus V. So we have then C is the length of W minus V. So C squared is W minus V dot W minus V, which, as we did before, length of W square plus length of V square and minus 2 V inner product W. Okay. Now, putting this in place, okay. Wait a minute, I missed something. Yeah. Sorry, I have 2 here. So let me correct that. So, okay, put this in the expression of the cosine here. And this gives you the result, because this says that when you replace c squared with this term, these 2 terms will cancel with these, and you will have this 2 times this thing equal to 2 times the inner product. So we get the result. Now, this tells us a very important thing. Okay. Namely that if the right-hand side, that is cosine alpha, is 0, then the inner product is 0. But what does it mean that cosine alpha is 0? It means that because alpha is between 0 and pi, alpha is pi over 2. Well, if this dot product is 0, but the vectors are not 0, you have the converse also true. So converse is also true. Okay? If the lengths are not 0. So this says that, okay, 2 vectors are perpendicular, equivalently alpha is pi over 2, if and only if their dot product is 0. Okay, here we adopt the degenerate case. If one of the vectors is 0, okay, then it's perpendicular to everything. So with that degenerate assumption, this statement is true for every Vn W. So to check perpendicularity of 2 vectors, it's enough to look at their dot product. If it is 0, they are perpendicular. If it is not 0, they are not perpendicular. So let us apply these things in some examples. Right. Now, the first one is a direct application. Find the angle between the vectors in space. V is 0, 1, 1, and W is 1, 0, 1. Okay, because of the zeros, you can determine this by sketching as well, but we will not do that. Okay, we will consider then by the theorem, okay, the dot product is length of V, length of W, cosine of alpha, where alpha is the angle between the two vectors. Well, we can calculate these one by one. V dot W is very easy, 0 times 1 plus 1 times 0 plus 1 times 1, so it is 1. Okay. On the other hand, the length of V is the sum of the squares, which is 2, under root. Similarly for W. Okay, so this says that cosine alpha is 1/2, so alpha is pi over 3. This is a direct application. Okay. As a second example, let us show that B is 2, 3, and C is 4, 2. Okay, determines a right triangle. Okay. Well, the hint is that consider BA dot BC. Okay, so what is the idea now? This time we don't calculate the side lengths, but we calculate directly the angles. Okay, we have 3 angles, okay, and we can calculate those one by one, but I mean the hint says this is the one, so let us cheat and check this directly. Of course, BA dot BC means the following. This is A minus B dot C minus B. Well, A minus B is -1 minus 2 dot C minus B is 2 minus 1. Okay. Of course, the inner product says -2 plus 2, so it is 0. Okay, so the angle between BA and BC, that is the angle at the corner B, is pi over 2. Or just BA is perpendicular to BC. So it's enough to say that it's a right triangle. Now, another very important consequence of the dot product is in projections. Okay, in space or in plane, okay, a projection is a vector parallel to a vector, okay, which is whose end is perpendicular to the given vector, in short. The projection of A on B is the following. You have an A, you have a B, okay. You drop a perpendicular and obtain C. Okay, say this is 0 or whatever, okay. Is the vector OC. So OC is a component of A, if you want, which is parallel to B. Okay. Now, how can we calculate this projection? Okay. But before we continue, let us observe the following. That the length of B is not important. So you see that here B only shows us a certain direction. Actually, there is even more to it. If B were in the opposite direction, okay, this figure would not change. So the only thing we know is that OC is parallel to OB, not necessarily in the same direction. Because when you drop a perpendicular to the vector B from this endpoint, okay, this B, even if it's on the other side, should be extended and you will have a perpendicular drop. Okay, norm, the direction. So neither the direction nor the length of B is important. Okay. But of course, that OC is a multiple of B. This is important because you are looking for a component in the B direction or minus B direction. That's not the point. Okay. So let us write down what we have. Firstly, OC must be a multiple of B. That is a restriction. And of course, when we look at the drop to C from A, AC is perpendicular to B. So these two conditions determine the vector C. Okay, let us start with the second assumption. So, okay, we have AC dot B, okay, equal to 0 in the first place because they are perpendicular. Okay. Now AC is C minus A, and C, or OC, is lambda B. So putting everything in place, we have lambda B minus A dot B, of course I have all arrows here. This is 0. Okay. But that means I have lambda times B dot B minus A dot B. But then lambda is then A dot B divided by length of B squared, because B inner product B is norm B squared. This tells us the projection is actually A dot B, B squared. Okay. B is the vector here. A is a vector, etc. So, okay, the projection, or C, is then A dot product B over length B times B over length B. Hence, okay, if U is B over length B, that is, if U is a unit vector in the direction of B, then the projection is A dot U, U, and length of the projection is just A dot U, of course, in absolute value. So, the length of the projection is the value of the dot product where A is, where we calculate A dot U, and the dot product gives us the length of the projection, basically, and B determines the direction. Okay. We will use these in our discussions with the distance calculations a little bit later. Okay. Let us now apply these in some examples. Actually, yes, I have more than one. Okay, let us find the projection. Okay, when we say the projection, of course, from the definition, it is actually a vector. So I don't emphasize it's the projection vector, but just projection. It means it's a vector. Okay, the length of the projection, of course, is a non-negative number. Okay. Of the vector A, 1, 1, 3, on B, 2, 2, 1. Okay. Now here, we are just supposed to apply the formula. Okay. Now, C, the projection, is then A dot B, okay, let me say just U, where U is B divided by length of B. Okay, we can calculate this directly. B is 2, 2, 1. And length of B is 2 square, 2 square, and 1 square under the root. So it is 1 over 3, 2, 2, 1. Thus, C becomes A dot 2, 2, 1 over 3 times 2, 2, 1 over 3. I'm putting the vectors. This is a vector. This is not. This is a scalar. And that is, of course, 2 plus 2, 4 plus 3. So that's 7 over 9, 2, 2. This is the projection vector as wanted In the second example, okay, we want to write the vector A, that is 1, 2, 1, okay, as a sum of two vectors such that V is, okay, U is parallel to the vector 1, minus 1, 0, and V is, right, V is perpendicular to this vector. Namely, the geometry is the following. Okay, we have A, okay, and we have the vector 1, minus 1, 0. Okay, well, I mean, it doesn't fit into the picture, so let me just say B. And we want to write A as a sum of two vectors, one of which is parallel to B, and the other one is perpendicular. So the parallel one is U, the perpendicular one is V. So this is nothing but calculating the projection. So take U to be the projection of A on B, and of course take V to be A minus U. Then A minus U will be just this V in the picture. So the whole thing is to calculate the projection, and thus U will be A dot, okay. Let me write it in the open form. So it is equal to that. Okay. Now my B here happens to be this one. So that is 1, 2, 1 dot 1 minus 1, 0, okay, divided by the length squared times 1 minus 1, 0, and this can be calculated. Okay, that would be 1 and minus 2, so that would be minus 1 divided by 2, 1, minus 1, 0. Okay. And B is certainly 1 to 1 minus half of 1 minus 1, 0, as in the process. Okay, we could have a direct approach also without using the absolute value. So alternatively, okay, what do we have? Say, okay, suppose we found U and V. The properties are the given ones. So U is a multiple of 1 minus 1, 0, because it's parallel to this vector. And V is perpendicular to this vector. Okay, so this is a direct approach. as an alternative one. Now, say V is ABC. Okay, well, this is U. Well, what does that mean? Of course, it means that we have A minus B plus 0 is 0, so A is B. Okay, that's the first condition coming from here. Well, secondly, U plus V is N. So this is 1, 2, 1. That was our A. And U is AA 0, because B is the same as A. Oh, sorry, that is C. Okay, C is not 0. And V is a lambda times, wait a minute, no, I mixed it up. V is this one, so it is AAC, and this is lambda times 1 minus 1 is 0. Putting them together, we can solve our problem directly. That is to say, we have lambda plus, okay, the first component is 1, minus lambda plus A. The second component is 2, and the third one's lambda times 0 plus C is 1. Okay. Now, solving, of course, we get from here directly that adding 2A is 3.5. Sorry, right. 2A is 3, so A is 3.5. Okay. So lambda happens to be minus 1 over 2. The sum should be 1. And finally, C is 1. Okay. So this says that our vector V, which is ABC, must be this one. A and B are the same, and C is 1. And similarly, you can calculate U. So a direct approach was possible.